Helicopter Flying Handbook 2-3 Aerodynamics of Flight. The pendular action inherent in a helicopter with a single main rotor, suspended from a single point, allows for longitudinal or lateral oscillations akin to a pendulum. Overcontrolling can exaggerate this pendular action, emphasizing the need for smooth and non-exaggerated control movements. The horizontal stabilizer aids in leveling the helicopter during forward flight but requires caution in rearward flight to avoid tail strikes, especially when moving rearward into the wind. Semi-rigid and fully articulated systems exhibit differences in pendular action, with the latter transferring centrifugal force to the fuselage due to its hard connection. Coning, an essential aspect of lift generation, occurs as the rotor blades assume a conical path during rotation, resulting from the interplay between centrifugal force and lift. The coning angle is affected by rotor RPM, and if allowed to decrease too much, it can lead to the blades folding up irrecoverably. The Coriolis Effect, also known as the law of conservation of angular momentum, dictates that the angular momentum of a rotating body remains constant unless an external force is applied. Gyroscopic precession, a property of spinning objects, influences the movement of the rotor blades in response to control inputs, occurring approximately 90 degrees later in the direction of rotation. This gyroscopic action is crucial for controlling the helicopter's tip path plane, impacting blade deflection and the overall dynamics of the rotor system. Vertical flight in a helicopter involves hovering, where the angle of incidence of the rotor blades is adjusted to control lift, allowing the helicopter to ascend or descend. The balance between lift and thrust against weight and drag determines the helicopter's vertical movement. In a no-wind condition, insufficient lift and thrust lead to a vertical descent, while excess lift and thrust result in vertical ascent. Transitioning to forward flight involves tilting the tip path plane forward, redistributing the lift-thrust force into vertical lift and horizontal thrust components. In steady forward flight, lift equals weight, and thrust equals drag, maintaining a balanced state. The helicopter loses altitude during forward acceleration due to the redirection of lift forward, but translational lift improves rotor efficiency, contributing to excess power. Pilots must adapt to changes in power or cyclic movement, ensuring a smooth transition to unaccelerated flight. In forward flight, airflow across the rotor disc varies, with the highest velocity over the advancing blade like 3 o'clock position and the lowest over the retreating blade like 9 o'clock position. The advancing blade experiences upflap, increasing lift, while the retreating blade undergoes downflap, decreasing lift. Understanding these aerodynamic changes is crucial for helicopter pilots to maintain control during different flight phases. Dissymmetry of lift is a critical concept in helicopter aerodynamics, referring to the unequal lift produced by the advancing and retreating halves of the rotor disc during forward flight. This dissimilarity arises from variations in relative wind speed across the rotor disc. The advancing blade experiences increased relative wind due to the helicopter's forward speed, while the retreating blade encounters reduced relative wind. To counteract the potential rolling effect caused by dissymmetry of lift, helicopter rotors incorporate mechanisms for blade flapping and feathering. Articulated rotor discs use a horizontal hinge, allowing individual blades to move independently, flap up and down, while semi-rigid rotor discs utilize a teetering hinge, causing both blades to flap as a unit. This automatic adjustment equalizes lift across the rotor disc. As the rotor blades rotate, they undergo flapping motions to compensate for dissymmetry. The advancing blade reaches its maximum upflap velocity at the 3 o'clock position, decreasing the angle of incidence and lift. Conversely, the retreating blade achieves its maximum downflap velocity at the 9 o'clock position, increasing the angle of incidence and lift. This flapping action helps maintain balance. Dissymmetry of lift becomes particularly noticeable during high forward speeds, leading to a condition known as retreating blade stall. To prevent this, pilots must avoid exceeding the never exceed speed or VNE. Blade flapping, along with cyclic feathering, plays a crucial role in achieving symmetry of lift during different flight phases. Pilots transitioning to forward flight from a hover or takeoff must be aware of the effects of dissymmetry, especially as translational lift becomes more effective and induces a pitch-up tendency. Continuous cyclic adjustments are necessary to maintain a constant rotor disc attitude and ensure a smooth transition into forward flight. Translational lift is a phenomenon observed in helicopter flight, where the rotor's efficiency is enhanced by gaining horizontal movement or utilizing surface wind. This improvement occurs with each knot of incoming wind, making the hovering rotor disc more efficient. As the helicopter transitions to forward flight, effective translational lift or ETL comes into play, typically between 16 to 24 knots. During this phase, the rotor disc outpaces the recirculation of old vortices, working in relatively undisturbed air. Effective translational lift results in reduced induced flow and drag, increasing the angle of attack and lift, thereby improving rotor efficiency. This enhanced efficiency persists until the helicopter reaches its best climb airspeed. Simultaneously, as the helicopter accelerates, translational lift becomes more effective, causing the nose to pitch up and the aircraft to roll to the right. These tendencies are a result of the combined effects of dissymmetry of lift, gyroscopic precession, and transverse flow. Pilots must be aware of and anticipate these effects, applying forward and left lateral cyclic input to maintain a constant rotor disc attitude during the effective translational lift transition. Translational thrust is another critical aspect of forward flight. It occurs as the tail rotor becomes more aerodynamically efficient during the transition from hover to forward flight. The improved efficiency of the tail rotor generates more anti-torque thrust, causing the aircraft's nose to yaw left for a main rotor turning counterclockwise. Pilots compensate for this yawing tendency by applying right pedal input. Additionally, the airflow affects the horizontal components of the stabilizer, contributing to a more level nose attitude. In the context of induced flow, rotational relative wind is generated as the rotor blades rotate. This wind flows parallel and opposite to the rotor's plane of rotation, striking perpendicular to the rotor blade's leading edge. This rotational relative wind is crucial for lift generation. As the blades produce lift, air is accelerated over the foil and projected downward, creating induced flow or downwash through the rotor disc. The downwash significantly influences the efficiency of the rotor disc. The rotational relative wind combines with induced flow to form the resultant relative wind. As induced flow increases, the resultant relative wind becomes less horizontal, leading to a decrease in angle of attack. The relationship between the chord line and resultant relative wind determines angle of attack, and changes in angle of attack impact the rotor's efficiency. In forward flight, the helicopter experiences a phenomenon known as the transverse flow effect. As the helicopter accelerates, induced flow decreases near the forward disc area and increases at the aft disc area. This differential in lift between the front and rear portions of the rotor disc is termed transverse flow effect, leading to changes in the angle of attack at different areas of the rotor disc. Specifically, the angle of attack increases at the front disc area, causing the rotor blade to flap up, and decreases at the aft disc area, causing the rotor blade to flap down. Due to gyroscopic action, the maximum displacement occurs approximately 90 degrees in the direction of rotation. Consequently, the helicopter exhibits a slight tendency to roll to the right as it accelerates through around 20 knots or encounters a headwind of approximately 20 knots. Transverse flow effect manifests as increased vibrations around airspeeds of 12 to 15 knots, occurring during forward flight or wind exposure while in a hover. This vibration, often felt just below effective translational lift on takeoff and after passing through effective translational lift during landing, is caused by the significant lift differential between the front and rear portions of the rotor system. Pilots may sometimes mistake this vibration for passing through effective translational lift. To counteract transverse flow effect, a left cyclic input may be necessary. In sideward flight, the helicopter tilts the tip path plane in the desired direction, causing the total lift thrust vector to act sideward. However, sideward flight can be unstable due to the fuselage's parasitic drag in the absence of a horizontal stabilizer for that direction. Higher altitudes aid in control, and the pilot must constantly scan in the direction of flight. The cyclic input in the intended direction controls the helicopter's movement and speed, while the collective and pedals are crucial for successful sideward flight. The collective prevents contact with the ground, and the pedals maintain the correct heading. Smooth and controlled inputs to the cyclic are essential, and the pilot should be mindful of the tip path plane's orientation relative to the ground. Caution is advised during sideward maneuvers to avoid potential hazards, as contacting the ground with the skids could lead to a dynamic rollover event with little reaction time for the pilot.